So Hubble's law, what actually this law states, the Hubble law states that the speed at which the galaxies are moving away from us is directly proportional to the distance between the Earth and the galaxy. Like example, when we observe the galaxies, say this is our Earth, this is our Earth, and see, say we have a galaxy 1 here, galaxy A here, the galaxy B here, galaxy C here, and galaxy D. All are having a distance, different distances from the Earth. Galaxy A is closer compared to that of B, then C, and then D. So according to Hubble's law, what it state that the speed at which because these galaxies are also moving. So what it state that the speed at which these galaxies are moving is directly proportional to the distance. Means those galaxies which are far away from us are moving much faster than those galaxies which are closer to us. So the galaxies which are closer to us are moving slower, and the galaxies which are far away from us are moving much faster. And the reason is like the gravitational field strength or the gravitational force decreases over the distance. Like if an objects are closer to each other, they will experience stronger gravity as compared to objects which are far. So that's why like those things which are far from us experiencing lower different gravity as compared to closer, that's why they have different speeds. So if two quantities are directly proportional, what should be the graph for two quantities which are directly proportional? So if we sketch a graph or plot a graph between the speed at which these galaxies are moving and the distance of the galaxy. So this will be a point for galaxy A. Galaxy A is closer, moving slower. Then galaxy B, then galaxy C, then galaxy D. So when we mark the point, means when we mark the point and draw a line, so it will always be a straight line which shows that the reflection speed of the galaxies is proportional to the distance between them. But this graph, because it's not like all the galaxies are following the same trend. Some, even they are closer to us, are moving faster. Some which are far from us may moving slower. But majority of them are following this trend. Majority of the galaxies, when we plot a graph, will like mark the points. Most of them are following this trend that those which are moving far from us are moving much faster as compared to those which are closer to us. So whenever two quantities are directly proportional, we replace with a proportionality sign and constant. So we can say V is equals to HD. What is H here? H is known as the Hubble's constant. So where V is the velocity at which the galaxy is moving, D is the distance, and H is the Hubble's constant, which is having a fixed value. But there is lot of uncertainty in this constant because lot of like information is lot of scattered data is there. So the value of the Hubble constant is not like accurate. It's there is a lot of uncertainty, and the value of the Hubble constant is about 2.2 into 10 to the power minus 18 second inverse. That's a value of the Hubble constant, 2.2 exponent minus 18 seconds. We can also use this Hubble's constant to find the age of the universe. So the idea is that what is the Hubble's law? It simply states that the galaxies which are away from us, Hubble constant is it's just a constant value. Like example, in mathematical equations, to balance one side, left hand side with right hand side, in a mathematical equation, we put a constant. So this constant is known as the Hubble constant. For every mathematical equation, like if I say x is proportional to y, so then we say x is equals to ky, where k is a constant. Same way for a Hooke's law, if you remember, we say force is directly proportional to extension. When we write F is equals to Ke, what is K here? K is known as a spring constant. It's a constant for the spring. Same thing, speed at which the galaxies are moving is directly proportional to the distance between them. And when we replace the proportionality sign, we replace with equal to and constant. And that constant is known as the Hubble's constant. So V equals HD. And Hubble constant is having a fixed value, which is 2.2 exponent minus 18 second inverse. How we can use this? Yeah, H naught is representing the Hubble. It's not only H, it is H naught, the Hubble constant. So V is equals to H naught D. Now, how we can use this Hubble constant to find the age of the universe? So we have the formula that V, finding the age of the universe, so if we want to find the age of the universe, we have the speed at which the galaxies are moving is equals to H naught D. Now, if I simplify this equation, V divided by D is equals to H naught. If you remember the formula for speed is distance divided by time. So speed divided by distance is 1 over time. So that is a reciprocal of time, 1 over time. So in place of V divided by T, I can write 1 over T. So I can say 1 over T is equals to H naught. Or if I need T, so T is equals to 1 over H naught, 1 over Hubble constant. And 1 divided by Hubble constant, the value of Hubble constant is 2.2 into 10 to the power minus 18. So when we divide them, what we will get? We'll get time in seconds, which is about 4.5 into 10 to the power 17 seconds. And this 4.5 into 10 to the power 17 second is equivalent to 14.4 into 10 raised to power 9 years. And 14.4 into 10 to the power 9 years, 10 power 9, that is a billion. So what we can say it's about 14.4 or 14.5 billion years. So that is the age of our universe. So if we want to find the age of our universe, we work out, we have the formula speed is distance over time. So according to Hubble's law, speed is equals to Hubble constant time d. So V divided by T, D is equals to Hubble constant. Right now, the value of according to the current value of the Hubble constant, the age of the universe is 14.4 billion years. But what will happen with the passage of the time, as we'll have more data, the value of the Hubble constant will change. So as the value of the Hubble constant will change, the value of the Hubble constant will decrease, so the time will increase, so means the age of the universe will increase. So V equals H naught D, or V over D is equals to H naught, and V over D is equals to 1 over time, or 1 over time is Hubble constant, or Hubble constant or time is equals to reciprocal of the Hubble constant. And reciprocal of the Hubble constant, when we substitute the value, we get the age of the universe. Yeah, according to this, if there is another universe existing and that is having another age, so the value of the Hubble constant will be different for that. Like it's having a different age. So here you have a simple calculation for a Hubble constant, because speed is equals to Hubble constant divided by d. So speed divided by d is equals to Hubble constant, and speed divided by distance or is equals to reciprocal of the time. So 1 over time is Hubble constant, or we can say the time is equals to 1 over Hubble constant. We just change the subject. Like we need time, so Hubble constant will be h naught. So we just substitute the value of Hubble constant and we get the time, and that time is known as the age of our universe. And that age will change as the value of the Hubble constant will change, the age of the universe will also change. There is a lot of uncertainty about the value of the Hubble constant. So This is the approximate age, which is 14.4 or 14.5 billion years. So it all started with a singularity, and there's all the things tend to move away from each other. And using the concept of a Hubble constant, we can determine the age of the universe. Is it clear, this one? Why 1 over time? Because as you can see, speed divided by distance is Hubble constant, and speed divided by distance, or velocity divided by distance, is 1 over time. Because speed is distance divided by time, so d is multiplied, other side will be divided. 1 over time is equals to speed divided by distance. So according to one equation, speed divided by distance is Hubble's constant. According to another equation, speed divided by distance is 1 over time. So when we compare, we can say the Hubble constant is reciprocal of the time, or we can also say time is reciprocal of the Hubble's constant. So when we substitute the value of the Hubble constant here, which is 2.2 into 10 to the power minus 18, we get the time, and that time is refers to the age of our universe. Then the galaxy, there is a Doppler effect. What is the meaning of a Doppler effect? The Doppler effect means when objects are moving away from us, the wavelength will increase. And when objects are moving closer to us, the wavelength will decrease. The Doppler effects is actually refers to a wavelength. Wavelength means like the distance between the crest, like if this is representing a wave, when we measure a distance between the two successive crests, that is called a wavelength. It's denoted by a Greek alphabet lambda. So according to Doppler effect, what it states, like we are here, we are the observer. Or example, this is a source which is emitting out the waves, and we are observing here, we are observer 1, and this source is moving away from us. So according to Doppler effect, when the source is moving away from us, the radiation which we receive, or the wavelength which we receive from the source, as it is moving away from us, that will become longer. And opposite will happen if there is another observer, observer 2 is there, and it is observing the source. As a result, when the source is moving towards this observer, the wavelength which is received, or the wave which is received by the observer 2, will be shorter. Like this wavelength will decrease for observer 2 and the wavelength will increase for observer 1. So due to the movement of the source, if the source is moving away from us, the wavelength increase, and if the source is moving towards us, the wavelength will decrease. This change in the wavelength due to the relative motion of the source or observer is known as the Doppler effect. And using this Doppler effect, the two things will happen. Like according to, like we are observing the sky and we are observing one galaxy which is moving, going away from us. So what we will receive, a longer wavelength or a shorter wavelength? This galaxy is going away from us. The wavelength which we receive.
Longer.
So it will be longer. And there is another galaxy. There is another galaxy which is moving closer to us. So what wavelength we will receive? We will receive shorter wavelength. So as a result, the galaxy moves towards and away from us. The wavelength which we receive from the galaxy changes, and this change is known as the Doppler effect. If the galaxy is moving away from us, what we call that we get a red shift. And if a galaxy is moving towards us, what we say? We say we get a blue shift in the wavelength. So red shift when the galaxy is moving away from us, and a blue shift when a galaxy is moving towards us. When we observe, most of the galaxies are giving us the red shift and few galaxies are giving us the blue shift. So from this idea, as most of the galaxies are giving red shift and few of them are giving blue shift, we can say so most of the galaxies are giving red shift and few of them are giving a blue shift. So with reference to that, we can say that the universe is expanding. Like things are moving away from each other. How we say universe is expanding according to this Doppler effect? Because the wavelength which we receive from the galaxies which are moving away from us as it get longer or giving a red shift is more, like most of the galaxies are giving a red shift than a blue shift. That's why we say the universe is expanding. So that is one thing, one evidence of saying that the universe is expanding, or for a the Big Bang as well. How does expansion of a universe affects the position of object? It is because of fabric space-time displays the object, or actually basically what happened, there is the energy which is driving the things away from us, and we call that as a dark energy. And there is a matter which is bring the things closer to us, that's called a dark matter. So in our space, as the dark amount of a dark energy is more, so we say that is responsible for driving the things away from us. So many factors are there. This is one of the reason why we say the universe is expanding, because most of the galaxies which we observe are giving us the red shift rather than the blue shift. Like example, this is a simple example. Say this is a galaxy. A person is observing from here. This galaxy is going away. So what he will observe? He'll observe a red shift. But there's another person, this galaxy is moving towards that. What he will observe? He will observe a blue shift. And most galaxies are giving a red shift. That's why we say the universe is expanding. And that is giving an idea of a Big Bang, that all started. What is the definition of a Big Bang? The universe, the space, time, matter, and energy, everything was created from a single point. Like what we see now, our solar system, different types of galaxies, they all were a single point. That is the point of singularity. And it was start to move everything, because the Big Bang, everything start to move away from each other, and the space, the matter, space, time, and energy, all as the result. Right now, like maybe the size of the universe is this, which is having lot of galaxies, and according to the Hubble's law, the age when the Big Bang happened, that is a single point is there about 13.8 billion years ago. It happened, and it expanding and cooling ever since here. Like, so as the galaxy progressed further, the observer experienced the blue shift, also start to experience red shift. But the observer, yeah, that's true. That like as it's moving further away from us, the red shift, like it's shifting more towards red. It's getting much longer. So example, say this was these are the lines. This is the line spectrum or absorption spectrum. Say this was a spectrum, means like group of colors is called a spectrum. So this type of a pattern we observe from hydrogen, okay, on Earth. An example, so example, this is what we observe for a hydrogen on Earth. Then there is also a hydrogen present on any galaxy, and we observe the same pattern, same trend is there, but it is shifted towards red. Like this is red and this one is violet. So this is shifted towards red, more towards red. So what we can conclude from this figure, like there is a hydrogen on the Earth, this type of pattern absorption spectrum it gave. And there is a hydrogen on the galaxy and it gave a pattern like this. The same similar pattern, but the lines are shifted more towards red. So what we can say about this galaxy? Is it moving towards us or away from us? So this spectral shift towards red shows that this galaxy is moving away from us. And if it was moving towards us, then what will happen? These lines will shift it towards blue. So it's a comparison between the absorption of line for hydrogen on the surface of the Earth and hydrogen in the galaxy. If it is shifted towards red, we say it's this galaxy is going away from us. If it's shifted towards blue, means this galaxy is moving towards us. Which galaxy is giving us the blue shift? The nearest galaxy. So our neighbor, the nearest galaxy, that is Andromeda, is giving us the blue shift because it is coming towards us. This is known as the absorption spectrum or a line spectrum. It's like on Earth, we have a hydrogen and this hydrogen is giving different amount of energies. When we sketch this result, say the pattern was, when we sketch this result, say the pattern for a hydrogen was 1, 2 and 3 lines. This is like absorption, like amount of energy with the hydrogen absorb or release. This is absorption, so it is absorbing. So this kind of pattern, or this is the amount of energy the lines are representing. What is the energy absorbed by hydrogen? This side we have say a violet color and here on red color. But there's a galaxy. Galaxies also, like stars also, they consist of mainly hydrogen or helium is there. So there is a hydrogen in the galaxy and we receive the energy from that hydrogen and we observe that that galaxy is giving a spectrum, absorption spectrum, same pattern as hydrogen, but that pattern is shifted more towards red. The lines are similar, but these lines are shifted more towards red. Close the same pattern, but lines are shifted more towards red. So it means which shift it is giving? It means it is giving a red shift. So if it is giving a red shift, what we can say about this galaxy, that how it is moving towards or away, because it's giving a red shift. So it means this galaxy is moving away from us. And there's another galaxy which is also having hydrogen emitting out or absorbing the radiation, and we observe that hydrogen spectrum, the absorption spectrum, the energy which this hydrogen absorbed, and what pattern we observe, the similar pattern, but that pattern is shifted more towards the violet or you can say blue. So what we can conclude from this, or what we can say from this, it is this was originally what happened on Earth, but different galaxies shift the pattern. So it means the wavelength is shifted towards the violet or blue. So it is giving a blue shift. So if a galaxy is giving a blue shift, what we can say that this is moving towards us. Is it clear? The blue shift and the red shift, and how we can conclude that whether it's moving towards or away from the absorption spectrum. So as you can see, another example, this is what we have on Earth. And this is what we are getting from the galaxy. So similar pattern, but shifted towards the red, it means this is moving away from us. So according to a Big Bang theory, it states that the universe start off with a very hot and very dense. It's maybe infinitely hot and infinitely dense singularity, and it expand ever since. So it's expanding. Like absolute size of a universe is not known to us. We only have an observable universe. Like we don't say that this is the size of the universe because we don't know. Maybe the light which we receive now is not from the planet, not from the galaxy which is the furthest. There are more galaxies which might be far away from us. So with reference to that, the age of the universe will change. And about the fate of the universe, but the black hole temperature infinitely dense. For a black hole, infinitely dense singularities are the black hole, but for them, infinitely hot as well. So very hot. The fate of the universe, we are at this point. We don't know what happened to our universe. We may have an open universe, like our universe will just continuously expand. We may have a flat universe. Flat universe means like our expansion will slow down and we might have a constant value, or we might have a closed universe. We might have a closed universe. Closed universe means maybe the universe will come back to that singularity, or we may have a big crunch. So big bang, opposite of a big bang is a big crunch. But these are like we are not sure, as we don't know the exact age of the universe. There is uncertainty in the Hubble constant. We don't know how much dark matter is there, dark energy is there, because dark energy is the energy which is driving the things away from each other, and dark matter is holding the things together. So we don't know how much dark matter or what is the composition or percentage of a dark matter and dark energy. So we are not sure about the fate of the universe. But there are possibility we might have an open universe that it will just expand forever. It might become a flat, like it expand or rate of expansion slow down and eventually it will stop expansion. And we might have a closed universe that it expand to its maximum point and then it again come back to the point of singularity, which is known as the Big Crunch. So these are like, this was the second topic about the star cycles and the age of the universe. So our sun, as an average star, it's mainly hydrogen and helium. These things can happen after all matter is not there in black. Not possible. It's not that case. It's not possible. The stable star shines because of the thermonuclear fusion. The sun shines. This is about the summary of what we have discussed. And the background radiation, the cosmic background radiations are basically the radiation which we receive from the space. We call background radiation. So these radiations are also giving us a black, about a red shift. It also shows that the universe is expanding. Like basic, the same idea that most of the things are giving a red shift, which give an idea that the universe is expanding. So this was about the space physics. So the parts we have, we started with the day, night, then the phases of the moon. Then we have the the planets, orbits, their orbits, the comets, meteoroids, asteroids. Then we have the stars, star cycles, the low mass star, high mass star, and then the Hubble's constant, how to work out the age of the universe by using Hubble constant, as well as how we can say our evidence of a Big Bang, like how we can say that actually, like the things which support the Big Bang. That is mostly redshifts are there, and the things are expanding. That's why it's giving a redshift. And the background radiations, the radiation from the space, are also giving us a redshift. That's also an evidence that the universe is expanding or supports the Big Bang.